Welcome to the satellite communication course. So today we'll see that how your received power calculation calculated for the satellite link. For the received power, we have to consider some particular effective area, and then for the given effective area, we need to see that what will be the antenna efficiency for this received power. So for this received power, we should know that what will be the antenna efficiency and what will be the power density. So if you see that power received is nothing but a what will be the total effective area, or we can say that area for this received antenna. Okay, that is about we have to see here, and we say that we must talk to what will be the received antenna. So that's why the received area of the given antenna, and then power receiving is depending upon that what will be the antenna efficiency and what will be the receiving antenna area, and then F is about a power density. So if you solve it, this AR here, so then we get that this one, and if you put what will be the value for this power density F is nothing but a PTGT by 4 pi r square that we have written. So if you see here, the equation becomes A into PTGT by 4 pi r square. Now why this come? Because we have A is equal to what? Effective area is nothing but what? Efficiency of antenna and that area for this receiving antenna. So that's why A, that is term. F is nothing but what? PTGT by 4 pi r square. And then we solve this, we'll get that the equation for the received power. Now this one is about a PTGT, that is for the transmitting antenna. Now our aim is about to receive the power at, we need to find out the received power at the receiving antenna. So we should have to find out what will be the effective area of this antenna. Now effective area of the antenna can be is depending upon that what will be the gain of that antenna. So we can write the equation for the gain is equal to 4 pi epsilon AE, that is the effective area of the antenna, and a lambda square. If you rewrite the term of effective area with respect to the whatever the distance here, so we'll have the effective area equations, and that will be with respect to the what will be the received antenna gain. So put that term here. So that becomes what we have the receiving antenna. Then we have this lambda term here. Okay. So this is about a factor we have obtained, that effective area is nothing but this one, just A is equal to what? Whatever the received antenna gain, lambda square by 4 pi. Okay, received gain of the antenna, then lambda square by 4 pi. This one is about a term for effective area, and then this term is about a flux power density. Now simplify this term. We'll rewrite the equation. Transmitted power, transmitting antenna gain, receiving antenna gain by 4 pi r and lambda. These are the term 4 pi r by lambda, and that bracket is nothing but square. And that term for the received antenna, that is nothing but the path loss here. Now we'll further solve this equation and obtain the path loss, or a free space path loss, or when we transmit the signal from the transmitting antenna, then here some power will be received, but some power from the transmitting to the receiving antenna, when we transmit the signal from the earth station to the satellite, then some power will be transmitted from the earth station to the satellite. So in that case, there may be a free space path loss. In this particular region, this will be the free space path loss. And that free space path loss is equal to 4 pi r by lambda square. Now if you further solve this equation with respect to what will be the velocity of light and what will be the wavelength here, that lambda is equal to nothing but what? C by f, We have the relation of lambda, that is wavelength, with respect to velocity of light and frequency, so that a transmitting frequency signal, uplink signal, will get the f value here for the transmitting signal, so that the path loss is depending upon that a frequency here. If we solve here, we'll get that the path loss is directly proportional to the frequency. If that frequency changes, the path loss changes, even if again it will be depending upon the distance between the transmitting and the receiving here. So now, if you write the value for this velocity of light 3 into 10 power 8 here, and then further solve this path loss equation in terms of a dB, that will be 20 log of 4 pi by 3 into 10 power 8. This one is about a factor, this one is about a constant factor. 20 log of r is the distance, 20 log of f is the frequency, that is uplink frequency. And this term is nothing but what? 92.44 dB. And this one is about a term for the your distance and the frequency there. Now from this equation, if you see that the r is nothing but in a particular frequency here, and that is in kilometer, and frequency is in terms of a gigahertz here. So both the path loss are, if you see that path loss is depending upon both these components, that is your distance from the transmitter to the receiver and the operating frequency. Because from the transmitting to the receiving station here, we can say that earth station transmitting the signal to the satellite. So in between that, when we transmit the signal, some spreading of the signal takes place, and that spreading from the transmitter toward the receiver, and some of the signal not reach to the satellite there, that will be spread in a space here. So that is nothing but a free space loss here. And that path loss is depending upon what will be the distance, and that path loss is nothing but the attenuation takes place inside this particular free space region. Or we can say that that is about a loss in a particular free space medium. That is nothing but a path loss. Then from this equation we can find out what will be the link equation. Then the link equation is nothing but what will be the received power in terms of, we can say that a transmitting antenna power, that is effective isotropic radiated power, and then what will be the gain of a receiving antenna, and then a path loss. So now we can write the equation of received power to obtain the link equation, so that we can rewrite in terms of the gain and a loss here. So generally we say that PR is nothing but what? A PTGT GR by 4 pi R by lambda bracket square here. Or we can write here the equation PTGT into GR by your path loss. That is about a LP here. So now if you see this equation here, this one is about a PTGT is nothing but the term that will be from the transmitting antenna, or this term is nothing but what? The EIRP. That is a effective isotropic radiated power from the transmitting station there. EIRP. Now if you express this term in terms of a decibel here, or a dB, you will get that this term received power, that will be in a dB. This will be nothing but a EIRP, effective isotopic radiated power, plus we have the term for the receiving antenna again, that will be GR, and that LP is in a denominator, so it will come the numerator here with a minus sign, so that we'll get that equation in terms of a dB watt here. So we know that EIRP is equal to nothing but a PTGT here, or we can say that that will be of a 10 log of base 10 here, and that will be what? A PTGT there. Similarly, we have the gain of a receiving antenna. That gain of a receiving antenna is nothing but a 10 log of 4 pi AE by lambda square. That is gain of a receiving antenna, and that is about in terms of a dB. This one is again in terms of a dB watt. Then a path loss, that LP is nothing but a 10 log of here base 10. Always you consider that is about a base 10 here. That is 4 pi R by lambda, and that will be nothing but the a path loss. Now we obtain this because this one is square here, so 20 log of this one. Okay, we get this equation in terms of a dB watt here, and this is about we say a path loss, or this one is in dB path loss, and it is depending upon that what will be the distance between the transmitting and the receiving station. Again, this is depending upon that what will be the free space loss, and all these equations we obtain, or we can say that a received power that obtained based on the ideal condition. But in practical, that equation is not true because we need to add some additional term here. That additional term that will be is related to the loss, and these losses are nothing but that losses at the antennas, losses at the, we can say that duplexer there, the losses at the whatever the we have the receiver there. Okay, or we have the cable there, losses there because of that a waveguide loss, losses due to the polarization mismatch, and again some losses there, and that all the losses if you consider together there, and that loss is become a system link margin. Okay, we can say that all the losses which are the all losses, that will be nothing but LM, and that will be nothing but the system link margin. That is about a practical case. We consider the all the losses, that is about the losses at the receiving antenna, losses in duplexer, even we have the filters there. Okay, band pass filter here. So losses due to the filter also, losses at duplexer, cable. Okay, likewise we have the losses. All the losses are combined, and that is nothing but the system link margin. And using that, we can find out the link equation. The link equation is nothing but what? PR is equal to effective isotropic radiated power, then a gain, then we have that path loss, then we have the losses due to the system link margin, or a, we can say that a marginal loss, or you can say that a system loss. And this is nothing but the link equation for the receiving antenna. Then this one is about a received power. Then we need to know about what will be the noise at the receiver. Why we need to consider the noise at the receiver? We need to obtain that what will be the carrier to noise ratio. Or we can say that we need to find out what will be the noise power at input there using this C by N. So we should know that what will be the noise power at the receiver. And that will gives us the C by N ratio. If we understand that what will be the noise power, then we can able to obtain the what will be the C by N ratio. And why this noise occur? And that noise is occur because of that there may be a changes in the temperature of the given component. In generally we say that at a 0 Kelvin K system work properly, all the components work properly, and about the 0 K there will be a temperature rise, and because of the temperature rise, that will be the noise, thermal noise at a 0 K. Okay, at a 0 K of a temperature. So then, okay, above this, below this, is it work? So above this 0 K, so there will be a temperature rise in the given component there. And because of that, it generate a noise. Because of the temperature, it will generate a noise. And that noise is depending upon that what are the various components in the receiver system. Because in a receiver system, there may be the receiver, IF, all the components, and each and every component they have some particular noise. And this noise is occur because of that increase in a temperature, because some objects in a system or some object in a receiver system, they change according to the variation in the temperature. Generally, we say that a noise is nothing but a random fluctuations of noise is nothing but what? A random fluctuation of whatever the electron component, or we can say that random fluctuations of the voltage or a current, and that will be due to the variation in the electron, or because of that variation in the temperature, there may be a changes in the temperature there. There may be variation in the electrons, and that's why that noise you can say that it is about a fluctuation of voltage, and that fluctuations of voltage around a 0 volt there. So if you calculate that this particular noise, and this noise is nothing but a what? A noise is of a Gaussian probability distribution function, and that will be a 0, and around that 0 your noise will be varying here. So this one is about your holds, and this one is about the Gaussian function at the 0 or voltage around the 0, it will changes. I mean, this is about a Gaussian distributions for the 0 mean, and noise voltage will changes around the 0. If you consider that this is about a time, so this is way we have the fluctuations of the noise voltage is occur, and that fluctuation is with respect to the around a 0 mean there, or around a 0. So low noise amplitude occur, that will be more frequently, and a high noise amplitude occurring less frequently, and they have the distribution that will be the Gaussian distribution around the 0 volt value. And if you consider that this particular noise and some other noise are again present in a system, and that noise is a flat spectrum, just like a white noise or this particular noise voltage as to the signal voltage that will be linearly there. So means we can say that that particular noise is nothing but a additive white Gaussian noise, and that will change linearly there. So we should find out what will be the thermal noise power density, and this thermal noise power density is nothing but the function of the temperature. So we can say that noise power density, that is about n0, is a function of a temperature. So we can write a noise power density that will be k into a t here, and this one is depending upon that what will be the frequency or what will be the operating frequency. So k is a Boltzmann constant, and that will be is equal to 1.38 into 10 to the power minus 23 joule per k. So we can find out what will be the noise power. So noise power is nothing but what? It is a product of a power density and the bandwidth. So you can write n0 into b. B is nothing but the bandwidth, and this bandwidth is nothing but what? We can write in terms of what? A k here, that t here, and a b here, ktb, and that will be a watt here. And that bandwidth is nothing but what? A noise bandwidth. Because if you see that we have the noise bandwidth, this one is nothing but what you can say that is about a noise bandwidth, and just this is about a small frequency that will be nothing but a n0, and that is about a thermal noise power density for a particular bandwidth region or a particular power. And this is nothing but a what we can say is a noise power density. So noise power is nothing but what? Is a function of a whatever the bandwidth of a signal, and this one is about a noise power density, and this is about a n0. N0 is equal to nothing but a kt, and that is depending upon that noise power with respect to the particular frequency there. Okay, so hertz here we can write. So that we'll get that a noise power that is nothing but a ktb, that is about a noise power n is equal to, we can say it nothing but a kt. Now this one is a noise power at the receiver. So if you consider that in a typical receiver system, because we say that this noise is generated and that noise is depending upon that a Boltzmann constant or what will be the temperature variation there, so that will get that noise power density. So if you consider the receiver system, in a receiver they have the various components, and if you consider generally the component of RF amplifier, a down converter, then we have the IF amplifier, a demodulator. So then we should have to calculate that the values of the noise power with respect to those particular components. There will be a noise from the one particular component. We'll just see that first. Typical receiver system, and the typical receiver system, this one, it has the antenna, then it has the RF amplifier, then down converter, then IF amplifier, then we have the demodulator, and now these are the components here. Means we have the basic is nothing but signal received from the antenna, then it will reach to the RF amplifier. So whichever the noise is present, that will get amplified here. Then the same noise further processed at the down converter. Then again it will reach to the IF amplifier. The same noise again amplified here, and then it will go to the demand. So if you see here, that noise is further processed in the receiver component. So that's why one by one, if you see that noise will be as compared to the single component, if you come complete, if you see the complete system, that noise will be larger. Okay, whole system. That that noise will be a very large. So means signal received by the antenna, then we have the amplifier. So the noise, whatever the noise is present, that will get amplified at this particular system there. So if at this particular receiver, okay, if that noise is low, so then overall system noise will be low. If that noise is large, then overall system noise will be large because that noise get amplified throughout this particular component. So the signal to noise ratio is depending upon that what are the various components present in a receiver system, or if you calculate that a signal to noise ratio for this RF amplifier, so that will be the noise present in this particular component, and then further that noise is propagating to the another component. So means this particular component is affecting all other components in the receiver system. So then overall receiver have the large noise, or you can say that that RF amplifier deteriorates your noise throughout the system there. So to understand or to get the noise to be removed, so we need to remove the noise at this RF amplifier itself. Or if we are not able to remove the noise at this RF stage, so then that noise will be propagating through the all the components. So then we can calculate that we need to remove the noise at the RF amplifier itself so that your system will not transmit the same to the all other components. Because whatever the changes occur at this RF amplifier because of the temperature, so noise will be adding, then the same amount of noise will be generating to the all other components. So that's why the whole system is to be considered, and then we need to consider the temperature of whole the system. So that temperature of whole the system is nothing but a system noise temperature, that will be the TS here. And this system noise temperature is depending upon that temperature of each and every component there. And from this we can find out a noise power. From this we can find out the noise power at the input of a demodulator, and that will be nothing but, here the noise power at the input of a demodulator here, that will be nothing but a GIF, because KTB here, that's why KT. T for the temperature of that IF component, B plus is about a first component, then next about a down converter here. So then a GIF, then GM, then KTM, then B, then another. This one is over now. Okay, we have a GIF, then modulator here because down converter. Then we have the GRF to GIF to GM, then KB here with respect to that TRF plus TE. Now, how this comes? Because if you consider that for a given particular receiver, that is about the input temperature for the receiver, and we have the RF amplifier, then the temperature, or you can say that a noise temperature for the RF amplifier, so that will be a TRF. Then it will further process to the ideal RF amplifier. So we have the gain, that is the GRF here. We can say that the ideal RF amplifier. Then we have the a temperature for the mixer because down converter here. So that's why we can say that the temperature for the mixer, and then we have the gain of the mixer. So that's why GM is the gain of the mixer. Then ideal converter, that is the down converter we have, or you can say that ideal amplifier, ideal mixer. Okay, converter, or we can say that ideal mixer. Okay, then we have the gain of a IF, and then this is nothing but a ideal IF amplifier, and then a power noise power at the demodulator. That will be the input to the demodulator. So here, if you consider that here, that is about a TIF, noise power, because of that IF here. Input to the RF, so because of the temperature TRF, that is about a nice temperature of the RF amplifier. The gain of that RF amplifier, consider that ideal RF amplifier. Okay. So next we have the down converter, that is nothing but a mixer. So that's why the noise temperature of a mixer TM, then gain GM for the mixer, ideal mixer here, or a converter. Then a noise temperature of a IF amplifier, then gain of a ideal amplifier, ideal IF amplifier, and that will be the noise power at the demodulator. So if you consider that overall system, that will be a TS and a noise power. And here we have the gain term of a GRF, then GM and a GIF. So that is about the system noise temperature. This one is about a TRF, is about a noise temperature of RF amplifier. This one is the noise temperature of mixer. This one we say that a noise temperature of IF. So that overall system, if you see that the noise power is at IF, because this one is about a noise power due to the IF. That is nothing but what? The gain of a IF. Okay. This one is about a gain of a IF. Then KTB term. K is for Boltzmann constant, T is for the IF amplifier, and B here. Then add this, because at this particular point here, we need to consider that gain of a mixer KTB here, and here the multiplying factor for the GIF, because we calculate here at the noise power. Then another here, gain of a RF amplifier and a KTB for the TRF and T. Okay, KT for the TRF and T and GIF and J. So now why these terms are adding here? Because initial, that is about a first term, we need to consider the gain of a GRF, and that gain of all other compounds are adding. So that's why GIF and GM, K bandwidth, and then a noise temperature. Then next, we calculate the gain at here. Okay, so that's why GM, the gain of that another term, because calculation is here. So GM and GIF. So that's why KTM. Next about a only the GIF. Okay, likewise. So that's why this total term, if you calculate that, and we can write with respect to that a system noise temperature, that Pn is equal to what? GRF, GM, GIF. Then we have the K. Then we have the system noise temperature and the bandwidth. And from this we can calculate that, or we can obtain the system noise temperature, that will be a TS. TS is equal to what? TRF plus TIN plus TM by GRF plus TIF by GRF to GM. That will be nothing but the system noise temperature. TS is equal to what? TRF plus Tin. That is input term here. That TM by GRF here. That is for the mixer. Multiplication factor from the gain of RF amplifier. Then TIF is equal divided by GRF into GM, because this one is about the gain of the initial component of RF amplifier and a mixer here. So that's why TIF by GRF and a GM here. Now this gives only the what we can say that noise source with a temperature that will present at the input of the RF amplifier, and that will generate that a noise power at the demodulator. That is about the PN. And here we have seen that a individual component, or a individual component noise, or a individual noise sources for each and every component that we have seen, and this gives us the system noise temperature. Then from this we can calculate the what will be the noise figure, and that noise figure is nothing but what will be the input signal and input to the input noise power. or you can find out the what will be the output noise power and all. Then using that noise temperature, we should know that a noise figure, and that noise figure is nothing but is the ratio of a input signal to input noise power to the output signal power to the output noise power. So SI is nothing but what? A input signal power. NI is equal to what? Input noise power. Then SO is equal to what? Output signal power. Then NO is equal to output noise power. Now this gives us the noise figure, and that will be the signal to noise ratio at the input side or at the output side. So generally we say that some device we are using, that device adds some noise itself. So that's why the signal to noise ratio, or you can say that output signal to noise ratio is less than the input signal noise ratio. So that's why the noise figure, if you see that a noise figure is greater than the 1 or greater than the unity there. Why? Because the signal to noise ratio at the output is always less than the signal to noise ratio at the input side. Because a devices add some noise itself, so that's why the output signal to noise ratio reduced there. So noise figure, then it will become say unity, or it will be greater than the 1. So if you write the term of a noise temperature, then a noise figure, that will be is equal to what? What will be the input signal and a noise at the input divided by a gain of a whatever input signal we have, then K, we have T0 plus Td into V. Now that is about a output signal here. So that's why we have some particular reference temperature, that will be T0, and Td is nothing but the device reference noise temperature or reference temperature. Okay, we have the noise here, the term we have forget here. The reference noise temperature and a device noise temperature. So that will get that a noise figure, reference noise temperature and device noise temperature, will get the noise figure. And if you further solve it, that term, so this one is about a GK here, K is we miss here. Okay, so this one is about T0, TD for the receiving, because for the output one. So you will get that